Hi, good day. Today's lesson is on the final chapter, chapter 7, which is decision tree analysis. This is the final chapter in this course, Engineering Economics of Oil and Gas Operations. Now let's get into this lesson. All right, so all project engineers are responsible to make the right decision on any types of project. So the process of decision making can be challenging because the choices can be overwhelming. So the decision tree analysis is an effective way of a structured decision making process, and the process allows the analysis of all possible consequences of a decision. So in this chapter, you will be able to understand the benefits of using this decision tree analysis, and then you will be able to also construct the decision tree diagram based on inputs from a project, and then you will be able to evaluate risks, assess probabilities and potential benefits of a future project based on the constructed decision tree diagram. All right, now let's start with a simple example. Let's say that you want to open up a food truck business and you have the options of selling churros or takoyaki. And if you sell churros, you can earn 100 bucks, for example. And if you sell takoyaki, you can earn 90 bucks. So which one would you choose? So in this condition, it's quite straightforward. You would choose to sell churros because you will earn more, right? However, what if the project fails? Because both projects say they have a 50% chance of success. And you have to take into account the cost of the project now. Let's say that the cost of churros is 30 bucks and the cost of takoyaki is the cost of takoyaki is $10. So how would you choose now? Now to do this, you can use a decision tree analysis method to decide on which one will be the project to choose. All right, so you want to start a food truck business, and your options are right now is either you open up a churro store, a churros food truck, or you sell takoyaki. And if you sell churros, you know that you will get 100 bucks. So that's your NPV, and that you have a 50% chance of success. And there's also a 50% chance of failure. And if you fail, that means that you will lose your cost of starting the business, which is 30 bucks. So your NPV is negative 30. For takoyaki, you also have a 50% chance of success and you will earn 90 bucks. However, if you fail and the failure rate is 50%, therefore you will lose your cost, which is $10. So your NPV is negative 10. Now to calculate the expected monetary value of the business is you multiply the chances with the NPV value. So say for churros, it will be 0.5 times 100 of the earnings plus 0.5 times the cost, which is negative 30, equals to 35. You do the same for takoyaki business. 50% chance times 90 plus 50% chance times negative 10 equals to $40. Now, which business would you choose? You would choose the one with the higher value, which is takoyaki, right? So this is a very simple example of how you use decision tree analysis to assist you in decision making. since we are in the oil and gas business, the options can be very overwhelming. All right, so you see there that the technique is very structured for decision making, and it involves drawing decision tree. So it's a graphical representation of a sequential decision problem. You incorporate logic, values, and probabilities. All right, when you draw decision trees, there are two types of nodes. First is the decision nodes. The decision nodes is typically indicated by rectangles, but some books use diamonds. So you have a rectangle, and that rectangle will branch into a complete set of possible actions. Like the previous example, it's your food truck, and then you branch into your churros or your takoyaki options. And then the next type of nodes is the chance nodes. The chance nodes is typically indicated by a circle. Some books use rectangles if they use diamond for the decision nodes. And then from that circle, it will branch into all possible results or situations. So from the previous example, the chance nodes would be the chances of the success or failure of each of the projects. Now, there are 4 steps involved in drawing the decision tree analysis. Okay, first of all, you draw the tree and you start with your first decision to be taken. You begin at the present and then you progress to the future. Like the present is, you want to open a food truck. So the future is what will be your earnings. And then once you have drawn the tree, you can now put in all of the values. So normally we put in NPV values to all the leaves of the trees. And then the third step is to estimate the probabilities of the result. This is where you put in all of the chances, whether it's 50% or 60% or 70% and so on. Once you have all of those values on the tree, then what you do is you roll back the tree. You evaluate at the leaves of the trees and then you work backward towards the trunk of the tree. So the value of the chance is the statistical or weighted average of all of its results, whereas the value of the decision is the optimum of the value of its action. It might not make sense now, so let's look at more examples. All right, first of all, there are 2 types of drawing decision tree. You can either do it horizontally or vertically. So the first method, if you do it horizontally, you create the tree from left to right according to sequence of event or decision. And then you do the decision making by solving from right to left. The second method is to do it vertically, where you create the tree from top to bottom, and then you solve from bottom to up. In this class, I would focus on the horizontal type of drawing a decision tree because it uses less space. All right, now let's look at an example from an EMP project. Let's say that you were to decide whether you should acquire a field or reject a field. So if you reject, then you don't get anything. If you acquire, then there would be possibilities, or you will have to decide whether you run seismic first or do you drill. Okay. If you run seismic, then there are chances that the results will be positive or negative. If the result is positive, then you probably decide that, okay, drill. Now, if you drill, there would be chances that you would discover a dry hole. Or you get a good discovery, or there's also a chance that you will discover a marginal field. If you do get a dry hole, what would you do? Would you drill again, or should you just abandon it? If you drill again, and then you will still have a lot more possibilities. If it's a good discovery, then you would just develop. If you find a marginal field, would you develop, or would you do further testing, or would you abandon it? If you do further testing, then probably there will be some other chances too. Right? So you can see that there are so many different consequences or probabilities of events happening if you choose uh, one over the other, right? Now, an important term in decision tree analysis is the expected monetary value, the EMV. So, expected monetary value is the product of its numerical outcome and its probability of occurrence. It weights the risk capital and chance of losing it against the potential rewards and the probability of achieving the awards. So you use a very simple formula. The EMV is equals to the cash value C times the probability of that occurrence, okay, P. For example, if you have an event and that it has a cash value of 1 million ringgit, and the probability of occurrence is 50%, meaning the probability of getting that 1 million ringgit is 50%. So therefore, the expected monetary value would be 1 million times 50% chance is equals to 500,000 ringgit. Okay, so this is what it means by EMV equals to the probability of that success times the net value of that gain minus with the probability of failure times the net value of the losses. And the rule is if the EMV is positive, then the risk-weighted reward outweighs the risk-weighted cost of failure. In other words, the rewards is higher than the cost of the failure. Now, if a decision has more than one possible outcome, then the EMV of the decision would be the cumulative of all the EMVs, meaning that the final EMV would be the cash value of one occurrence times the probability of that occurrence, and then plus the cash value of a second occurrence times its probability, plus C3 times P3, and so on up to Cn times Pn. Here's an example. Let's say if you toss a coin and gamble on the outcome. So the coin is balanced and it has two different faces. You have your head and your tail. So the probability of getting head or tail for a single toss is 50%. Let's say that player A wins 100 ringgit when the coin shows head, and he will lose 100 ringgit if the coin shows tail. So therefore, the EMV for player A is 100 ringgit of winning times 50% chance plus negative 100 ringgit due to losing times 50% chance, and therefore you get 0. So here you can decide whether you should play this gamble on tossing a coin, or should you just not do it. In this case, since the EMV is 0, that means that it will be a waste of time for you to do it. Okay, now let's look at one example. The exploration department needs to decide on to drill a prospect, and the basin study shows that the probability of oil discovery is 20%, and if successful, the contractor's NPV would be 50 million, or else if it's a dry well, then the cost will be 10 million. Should you recommend the prospect? Now, if we draw the decision tree analysis diagram, then you will start with the square, and then you are to decide whether you drill the prospect or you do not drill. If you drill, it says that there is a 20% of discovery and your NPV is 50 million. So therefore there is an 80% of finding a dry well, and if that happens, then the NPV will be minus 10 million. Now you recommend the prospect. So first of all, you have drawn the tree. Now to solve it, you roll it back from right to left. So let's do the first branch. So the first branch, you calculate what is the EMV for the first branch. So the EMV for the first branch here would be 20%. Let me write 20% of discovery times 50 million equals to 10 million. So that's the EMV of the first branch. For the second branch, the EMV would be 80% chance times the NPV minus 10 million, which is 8 million. And then you roll back further, so that's why I showed here the EMV is equals to 10 for the first branch, the top branch, and the bottom branch here is EMV is 8. So you roll back further whether you should drill the prospect. So the EMV, the total EMV for these two branch will be 10 minus 8 equals to 2. Just this. Now, what about if you don't drill? If you don't drill, that means you don't have any monetary values. You didn't pay for anything. You didn't do anything. Therefore, you don't get anything. So therefore, your EMV is 0. So now you can decide whether you should drill or not, since this EMV is 2 and it's greater than 0. So therefore, you say that you recommend that you drill this prospect. Okay. Another example, the exploration department intends to drill a prospect in central Laconia named as Kumang. So the basin study shows that the probability of gas discovery is 30%, and if successful, the contractor's NPV would be 20 million, or else the dry cost is 5 million. So you recommend the prospect. So again, we draw the decision tree diagram. You start with the decision with the square node. So you have to decide whether you drill or not to drill. If you drill, you have a 30% chance of discovery and your NPV will be 20 million. So that means that there's a 70% of failure to find a dry well, and your NPV would be 5 million. So you calculate the EMV for the top branch. The EMV for the top branch would be 30% chance times 20 million equals to 6 million. So that's the first EMV. So the bottom branch EMV would be 70% chance times the NPV of negative 5 million equals to 3.5. Okay, negative 3.5. So that means that you roll back further to see whether you should drill it. So therefore, the EMV of drilling the prospect would be 6 plus negative 3.5, which is 2.5. If we compare the EMV of 2.5 with not drilling anything, you're not doing anything, which is EMV 0, that means this is greater than 0, greater than not drilling, so therefore you can recommend that you should drill the prospect. Now let's try on an exercise that is a little bit more complicated. As you can see from the screen here, the question itself is long and it's a whole slide of information and words. So this is when students start to panic. But don't worry, let's try to digest and extract all of the infos from this exercise. Now, for example, say that you have a company called UITM Oil and you have just finished the FDP study of reservoir A. Okay, so you have reservoir A and then you justify that you will need a small platform and the small platform will cost 150 million to produce the reserve. And that small platform, okay, would make a revenue of 500 million. So that's your revenue from reservoir A. But at the same time, there is also another prospect from reservoir B. Okay. So just now you justify already, you're drilling reservoir A, but then now you say, oh, there's another one, reservoir B. It has been discovered last year, and it has gone through geological and geophysical study, including seismic inquiry. So the company is optimistic that reservoir B would generate additional income with probability of 40%. So you see here, additional income, probability of 40%. Meaning that they're drilling A, reservoir A, but now they want to do reservoir B too, okay? Because it will add to the income. And the probability of success is 40%. If reservoir B is a good producer, okay? And it will increase 20 million to the revenue. Meaning now, if they drill both, you will get 500 million. Right, 500 million, oops, plus 200 million. Okay. But if reservoir B is producing, then the small platform would not be would be inadequate for both reservoirs. So that means that they will have to install a larger platform, okay, with capacity for both reservoirs, and the cost of installation of the larger platform is 225 million. So meaning the cost will also increase because you have a bigger production. Alright, so reservoir B, there's another sidetrack that could be drilled through reservoir B to provide better indication of the economic potential of the reservoir. The reliability of the sidetrack well is 0.8. And then with this sidetrack well, you can add another 50 million of revenue. Okay. So to drill this additional sidetrack well is 10 million. So construct a decision tree analysis for this case, whether to produce A only or do both. And then assuming that you will proceed to drill both A and B, determine the EMV for the lowest case and the highest case. And then from the results, decide on which one to produce or to decide on your decision. Okay, so firstly draw the decision tree diagram, and then on diagram you have to assign the chance nodes and the decision nodes. So first of all, you start with the square node, which is the decision node here. So this is the square node, And then here you are to decide whether you are going to produce just reservoir A or produce both A and B. If you produce reservoir A, then you have your EMV, because you were already given just now. Your cost would be, what was the cost just now? I think it was the small platform is 150 million, right? And then you will get a revenue of 500 million, right? And then your revenue is 500 million here, so therefore you can calculate your MV1. But if you produce A and B, there's a possibility that B would be successful or not. So if it is successful, and we know that the information given that there's a 40% chance that both A and B will be successful. So that means 60% chance that only A is producing but B is a dry hole. So this is when you assign EMV2 here. Okay. And then if it is both producing, then you can also add a sidetrack, or whether you put a sidetrack or no sidetrack. With a sidetrack, again, the sidetrack can be reliable or not reliable. So the informations are all given. If it's reliable, it's 20%. It's 80% reliability. So that means 20% not reliable. And then the information also provides data about the cost, right? If for a small platform it's 150 million to install to produce both an A, that means that you need to have a larger platform, and that larger platform would need an additional, was it 225 million additional, so more cost there. And then however, if you're producing both, that means you have more revenue, but with sidetrack, then you have to drill an additional sidetrack well, which costs more. And then even if you put a sidetrack, it can be reliable or not. So you name all the EMVs at the ends of the branches. So you name here EMV1, EMV2, EMV3, EMV4, EMV5. Now all the nodes, the circle nodes here also have its own EMV. If you plus both EMV4 and EMV5, then it will give you EMV6. Combining EMV6 and EMV3 will give you EMV7, and then you plus EMV7 plus EMV2 equals to EMV8. And now to decide whether you produce A or produce A and B, you will compare between EMV1 and EMV8. Okay, so from here you can also put in all the values from the question. You can put in all of the costs and the revenue, but then it will be a bit tricky and messy. So it's advisable that you do this in a table form like this. So you create a table to calculate the EMV for each of the branches. So the table looks like this. First of all, you have a first row, which is the rows of events, because you have many possibilities. So for the events, you have event 1, 2, 3, 4, 5, based on the 5 EMVs. So the event 1 is to just produce A, and then event 2 is to produce A and B, but with a dry hole, and then or both A and B is producing. And then if even if both A and B is producing, you can have a sidetrack or not have a sidetrack. If you do not have a sidetrack, then you have also you put in all of the values later. So it's either you have a reliable sidetrack or a not reliable sidetrack. And then you put in the P values, the probability of successes, the chances. So producing dry A, you know, it's just only a 1 chance. And then it's given in the example that the cost of drilling, the cost of installing the small platform is 150 million, and then it will give a revenue of 500 million. So that means the net cash flow for reservoir A is 500 minus 150, which is 250. Okay. So that means the EMV, the expected monetary value here will be 350 times the chance, which is 1, equals to 350. So that's the first branch just now. So for the second branch to produce both A and B, you have two probabilities, whether it's B is producing or B is a dry hole. If B is there's a 40% chance of it producing, right? So that means it's 60% chance that it is a dry hole. And then remember that the cost of producing B now is it says that there's an additional what was it just now? The total cost of the bigger well, because the small, I mean, a bigger platform, the small platform is not is inadequate. So the larger platform will cost 225 million. So 225 million for these two events. But if but it is producing, you get an additional 200 million of revenue. So that means 500 plus 200 equals to 700. However, if B is a dry hole, that means you don't have an additional revenue. Your revenue is still 500. However, there's an increase in cost. Okay, so here you can calculate the net cash flow. You see the net cash flow here for the dry hole is lower now than just producing A, because you have additional costs to build a large platform, but then you don't have additional values. And then you calculate what is the expected monetary value, which is the chance of 60% chance times 275 equals to 165. Okay. All right. So what if B is producing? So you have both A and B producing. You have a bigger revenue. So your net cash flow is 475, and your chance, your expected monetary value is 190. Now, if B is producing, you can either have a sidetrack or no sidetrack. Oh, well, however, they want to drill a sidetrack. So to drill the sidetrack, remember the question says that it will incur an additional $10 million to drill the sidetrack well. So additional 10 million, that means see here the cost here has increased 10 million, 235. And it says that the sidetrack may be reliable or not. So the reliability of the sidetrack is 80%. Okay, so that means there's 20% is not reliable. And you can see here, you have to combine the probabilities now, okay? Because you're basically, for event 4 and 5, they're basically from event 3. You're just branching out event 3 into 4 and 5. So that is why the probability of event 3 is 0.4. So that's why these are 0.4 here, because these are from event 3. But each of the consequences has its own probabilities, which is 20% and 80%. Okay, so that means the total probability will be 0.2 times 0.4 equals to 0.08. And if both A and B producing and with a reliable sidetrack, so it's 0.8 times 0.4 equals to 0.35. Okay, so again, like I said, you have additional 10 million here to drill the sidetrack, so the cost is 235. If the sidetrack is not reliable, that means your revenue stays at 700. But if it is reliable, you get an additional 50 million on that sidetrack well. Okay, and then you calculate the net cash flow, and then move on to the EMV for each of the sidetrack cases. So now these are your EMV1, EMV2, EMV3, EMV4, EMV5. Now, to roll back from right to left, so you combine EMV5 and EMV4 to get EMV6, which is 202 million. To get EMV7 is EMV6 plus EMV3. So this is 202 million plus 190 equals to 392. And then to get EMV8, it is EMV7 plus EMV2, okay, equals to 557. All right, it says that to compare, so the lowest case, A and B is producing, but sidetrack is not reliable. So EMV4 equals to 37.2. This is the lowest case, right? The lowest EMV. The highest case will be produced from A only, and the EMV is 350 million. Okay. All right, but to make a conclusion whether to produce just A or both A and B, then you compare between EMV8 and EMV1. So after calculation, EMV8 is $557 million ringgit, compared to 250 million ringgit. Therefore, you will choose to develop A and B because EMV8 is greater than EMV1. Alright, so that is all for today's class. So the next class we will do some tutorial, a lot more examples on decision tree analysis. Thank you for your time.